The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's get started. One announcement. Test 3. It's a celebration of learning. It's going to be on Wednesday, which means no lecture. No lecture Wednesday. Instead, the celebration. Please go to your rooms as assigned here. If you're writing at 11 o'clock, you're probably in this room right now, and those are the room assignments. They're the same as for Test 2, but not the same as for Test 1. We moved more people out of 10250, give a little more room here, and there's plenty of room in these others. Those that write at 1 o'clock do not go to the normal lecture room, 6120. We're writing in 26100. And the coverage is right here, so that's up on the website. So you should know what we're going to be examining you on, and the same comments that I've made before. You know, I want to give you feedback, let you know how you're doing, whether your study methods are effective or not. It's not an attempt to retest your admission to MIT or anything like that. If you've done your work, you should do very well. And if you haven't done your work, you shouldn't do very well, and we'll be able to tell you so. So just remember what we've said in the past. Please take some time, read the whole exam. Do the easy questions for you. The ones that you find easiest, do those first. But let's be honest. You know, this isn't high school anymore. So, I mean, I had some people tell me after the second test, you know, I had my aid sheet, but I hardly used it. Well, think about it. Do you think I'm going to give you an aid sheet and then give you a question that requires you to take something off the aid sheet and transfer it to the answer paper? It's not pattern recognition. I mean, this isn't medical school, for crying out loud. You know, you got to think here. You got to think, right? So, you know, and this is now the third test. And it's going to be more and more thinking and less rote, although we'll have some confidence builders on there. I don't want to knock people off their balance. So work parametrically. Try not to immediately start punching in numbers. And if you don't know how to do a question in great detail, write me an outline. Tell me what you'd do. You'd equate some energies, or you'd minimize something, or maximize something. Give us a sense that you have a grasp of the material. And keep your eyes on your own paper. And our effort is going to be to get those graded on Wednesday and back to you in recitation on Thursday. So I think that's, and remember, please bring your 5 items. We're having more and more people showing up, minus periodic table of constants, something to write with. I've had people ask me for pens, for calculators. No one has asked me yet for an aid sheet, so I haven't had to help anybody on that one. Okay? Good. Well, today what I want to do is start a new unit. I want to talk today about organic chemistry. Now, this is going to be the most minimal introduction to organic chemistry. The reason we talk about organic chemistry at all is in order to prepare ourselves for more solid-state chemistry. Specifically, we're going to talk about polymers, and ultimately we're going to talk about biochemistry. Because even though this is solid-state chemistry, we as living beings are solid-state devices. We're made of soft matter. This is a polymer. Right? And this is a semiconductor, band gap of 2 to 3 electron volts, but it's not made out of 3-5 semiconductor. Nature's figured out a way of doing this without inorganic means. So we need to know a little bit, but if you really want to know organic chemistry, you're going to have to take 512. So I can't teach you in 50 minutes what people teach in one semester. So let's get a few definitions under our belts. Organic chemistry is the chemistry of compounds containing both carbon and hydrogen. Not just carbon, carbon and hydrogen. So diamond, graphite are not organic because they contain carbon but not hydrogen. And what makes these two elements special that that they figure so prominently in living organisms. First of all, hydrogen. Hydrogen is the element with the lowest atomic number. Lowest atomic number. And when it loses its electron, it changes character dramatically. We talked about this in recent lectures where we have simply a proton. It's capable of forming covalent bonds, but when it finds itself in a compound forming a covalent bond with something that's strongly electronegative, it's so denuded of electrons, even in the covalent bond, that that protonic entity can start mischief and form hydrogen bonds. Carbon's dead center, 4 valence electrons. So it's nowhere near metallic, it's nowhere near non-metallic. So it's got an intermediate value of average valence electron energy. It's very unlikely that carbon is going to acquire 4 electrons and become C4 minus, or lose 4 electrons and become C4 plus. It's prominently a covalent player, but it's very small. And because it's small, it can form multiple bonds. It forms multiple bonds. We've already seen evidence where it forms sigma and pi bonds. So it can form double bonds and triple bonds, not only with itself, but with other elements, notably nitrogen, oxygen, phosphorus, and sulfur. And even though silicon and germanium hybridize, because they're not small, silicon does not form double bonds. You will not see silicon analogs to carbon compounds throughout. Yeah, silicon sp3 hybridizes, and single crystal silicon has the same crystal structure as single crystal diamond. But that's pretty much where the similarity ends. It's pretty much sp3 hybridization, and that's the end of the story. So these two have very special qualities that make them so important. And I mean, the other thing that carbon can do is it can continue to link with itself and form chains and various other structures, and we're going to meet a few of those today. There are millions of organic compounds. Millions. I should say billions, billions, and billions. But I'm not going to cover all that. We're going to cover the ones that are most germane to our subsequent discussions of polymers and biochemistry. So let's first of all go through the taxonomy. So, I mean, I've posted all this at the website, and it's in the reading. I've tried to characterize this in a way that, or categorize it so that it makes some simple sense as opposed to just standing here and barking out a litany of facts to you. So the first thing I want to do is look at the left-hand column called the alkanes. And these are hydrocarbons. The whole thing we're going to look at is hydrocarbons for starters. Okay. And these, as the name implies, are compounds that consist of only carbon and hydrogen. Compounds containing only hydrogen and carbon. And the first group that we're going to look at is the alkanes, as you can see in the slide. And these are characterized by sp3 hybridization on the carbon. All the carbons are sp3 hybridized, and so that gives us the maximum possible number of bonds, maximum number of carbon-hydrogen linkages, maximum number of carbon-hydrogen linkages. And so the chemical term for such compounds is saturated. These are saturated hydrocarbons. And all of these bonds are sigma bonds. All the bonds are sigma bonds because they're all single bonds. All sigma bonds. So these are the characteristics. And the general formula, if you go through the math, is going to be C, some sub n number, whatever the number of carbons in the molecule. And then if we go through sp3 hybridization and put hydrogens at all the non-carbon linkages, it'll be H 2 times the C number plus 2. And so these are called alkanes, and this is the way you build the name. The nomenclature is it's going to have an ane ending, which is going to indicate that we're talking about sp3 hybridized hydrocarbons. And then, in order to indicate the number of carbons, we call out the carbon number by the prefix. So this prefix identifies the carbon number, and they're shown here actually. Let's take a look at a set of those. This is right out of your reading, and there they are, 1, 2, 3, and so on. And it's basically meth, eth, prop is 3, bute is 4, and these are all historical. And you can go into the reading and figure out butyric acid is one of the elements in rancid butter and so on. So there's some historical reasons. But after you get to 4, it's strictly the Latin ordinals. From here on, this is pent. And what do we have? We have hex, hept, non, dec, and so on. So just go back to your Latin and you're going to be fine. I'm not going to expect you to pull these out of memory. I would tell you, C5. Well, you've forgotten your Latin? Was it a requirement, an admission requirement? How many semesters of Latin did you need in high school to get into MIT? None. Okay, so I think I better keep that in mind. So I will tell you pentane, and I'll give you the formula, C5H12. All right, so these are also called straight chain molecules because if we look at them a little bit more carefully, we'll see the following. Let's have a look at what they look like. Oh, before I go, I just wanted to, hearken back and show that there's some overarching theme here. So these are 3 hydrocarbons that I've chosen. Propane, which we know is used as a fuel in, among other things, transportation and even in domestic barbecue grills. And it's a gas at room temperature. These are all the same. They're long chains with hydrogen around them. Okay, these are all symmetric molecules. Octane, which is the principal constituent of gasoline, is a liquid at room temperature. And icosane is a solid at room temperature. So all of these they're symmetric molecules, and the only thing that's happening as you go to larger and larger molecules is you're increasing polarizability. Your van der Waals bonds between molecules of the same identity increases, and you can see that as the molecular length increases, the molecule converts from gas to liquid to solid. So something to keep in mind. So these are the ball and stick images. Methane we've met before. There's the sp3 hybridization, 4 bonds, 109 degrees apart. In the case of ethane, this is C2H6. One of the 4 bonds is a carbon-carbon bond. It's a sigma bond. Okay? And then we go to propane. So now we've got C3. So that's what's cueing us in on which of these to choose. But I want you to note that at propane, this sp3 hybridization requires that as we add more and more carbons, if we're going to put one more carbon, we're going to put it up here, you can see that even though this thing is straight, it in fact at the local level is zigzagging. At the local level, there's some zigzagging, so we want to keep that in mind. The sp3 hybridization, sp3 hybridization gives bonding along the chain that in fact zigzags. And this is a 109-degree angle. And so if you're up really close, you say, well, this is clearly bent. But if you make this long enough and you get far enough back, in a general sense, this is termed a straight chain. It's a straight chain hydrocarbon. There's one other thing that is similar to what we've seen in the past in the case of silicates, and that's shown here. As long as we've got 109 degrees along this axis between the other bonds, there's no specification what happens down here. So this should remind you of what happens in a silicate when the oxygens don't all line up. And so it's possible to get disorder. And so here you see one case where you have the hydrogens on adjacent carbons not facing one another, whereas here they're lined up. So if I were to look on end from the left down the chain, I would only see one. All of the hydrogens are lined up, and we call this configuration an eclipsed configuration. This is slightly high energy, whereas this is a little bit lower energy, staggered. And what's the effect of that? The effect is not to give us a straight chain that goes in a B line. For that, you'd have to have the eclipsed configuration. Here's two examples of C17H36. They're both straight chain, but because one's twisting a little bit more than the other, and here I'm talking about just the carbon-carbon bond twisting, these are both termed straight chain, but they have different conformations. So this is starting to make you think about the plurality of possibilities, even within the same chemical composition that would be present in polymers. Here we've only got 17. Imagine if instead of 17, it became 17,000. What this can do. So this is an example of what we mean by straight chain, but it doesn't mean that it's a rod-like entity. Okay, but I can now show you something that's not a straight chain, so let's also look at something called a branch chain. Branch chain. Now that's different, and let's go look at one. I'm going to look at butane. Butane. You know, that's a gas at room temperature. It used to be used as a fuel for cigarette lighters, but I guess that's not PC anymore, so I don't know. Oh, now you can use it for lighting candles, right? You can use it for lighting candles. I can say that, can I? We'll light candles with it, all right? So let's look at butane. So that's number 4. So, all right, so just to smooth things along, it's possible to just write them in a straight line, even though we know these are 109 degrees. And we know that if there's nothing put at the end of the stick, we assume it's hydrogen. So all of these are carbon-hydrogen linkages. So I've got 1, 2, 3, 4 carbons, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is, as it should be, C4H10. And certainly this is identical to something that could be represented as follows. All right, so now I'm going to have the 4 outlining a tetrahedron. So there's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Remember, when you're in carbon chemistry, 4 sticks off of every carbon. That's what you're checking. Okay, so this is the linear. But there's another way we can do this. We can do the following. We can put, and off one of the carbons, I can put a branch. And then I've got to use the 4-stick rule. So 1, 2, 3, 1, 2. So 1, 2, 3, 4. This has 1, 2, 3, 4. So now let's count. 1, 2, 3, 4, 4 carbons, and 3, 6, 9, 10. 10 hydrogens. So on a formula basis, this is also a butane, but it's a different. You know, as solid-state chemists, we're very much attuned to molecular structure. And this molecular structure, the linear one, is different from this one. This is a branched one. So this one's called isobutane. Isobutane. And the other way to look at it is, well, the backbone is only 3 carbons. So if the backbone's only 3 carbons, according to this rule, this should be some kind of a propane. Another way to name this is to call it a propane. All right? But it's got, instead of just hydrogens, one of the propane side groups, instead of being a simple hydrogen, has this CH3, which is a methyl group. So we could call this one a methyl propane. And we could further number the carbons from left to right. So the first one is the number 1 carbon, the second is number 2, the third is number 3, and the methyl group is attached to the one in the second. So this is 2-methylpropane. And what we have here is 2 identical chemical formulas, but 2 different structures. And so, we all have sigma bonds everywhere. So we call these isomers. These are called isomers. But they're an isomer of a particular kind. They both have the same chemical formula, but what we can do is we can look at the constitutive groups here. So what we can do is say, here's a CH3, here's a CH3, and here's a CH3. And that leaves this one, which is a CH. Whereas over here, I've got a CH3, a CH3, and in the middle, 2 CH2s. These are units. Some people call them constitutive groups. Constitutive groups. So here, the constitutive groups are different from the constitutive groups in the linear configuration, and so these are called constitutional isomers. Constitutional isomers, because they have identical chemistry, but different constitutive groups or constituent groups. And so we can see this. Other thing that I need to introduce you to. Okay, so this is the same. This is just the methylpropane and the straight chain butane. Down towards the bottom, there's something called ethyl, and that's a radical. So we need to know the radical terminology. The radical is a species. It's a species with one or more unpaired electrons, with one, in some cases more, unpaired electrons. So unpaired electrons living in an orbital, that's a broken bond. So this is very highly reactive. This is highly reactive. Okay? So this is, if you like, think of it as a broken bond, highly reactive. So we need to know these, and the ones that we need to know are these little units that I've just been drawing. These little units. So if I take methane with 4 hydrogens, and I break one of the hydrogens off, and now I have a single electron sitting here, this is capable of being attached to some other species. In this case, it was attached to the carbon backbone. So this radical that comes from methane is called the methyl radical. Methyl radical. Another way to denote it is with the dot up here indicating that there's an unpaired electron. Obviously, the unpaired electron is on the carbon, but in the nomenclature of organic chemistry, people are fairly quick to make the necessary change. So if you see that, no one's suggesting that the electron's attached to the hydrogen. It's just a shorthand for it. This one here, the CH2, that we see over in the straight chain butane, this one is called, in this case, there's hydrogens above and below, so there's 2 unpaired electrons here. So they can then link up with carbons on either side. So that would be designated as follows, or if you want, CH2 with 2 dots, and this is called methylene. This is the methylene radical. And then the only other one that I really care about in the alkanes is the one that comes from ethane. C2H6 is ethane, and so the radical from this would be C2H5, and this is called the ethyl radical, and we'll come across some compounds. One that we meet socially is ethyl alcohol, where we put the alcohol functional group on the end of the ethyl. So that gives you an introduction to alkanes. So now let's go back and look at the next column. That's the alkenes. So now we're going to look at unsaturated hydrocarbons. And the first example is the alkenes. And these are characterized by sp2 hybridization. So that means at least in one place, it only takes one, at least in one place in the molecule there's a carbon-carbon double bond, and that will give you, if all we have is the one carbon-carbon double bond, it will give us the chemical formula CnH2n, and clearly n must be greater than or equal to 2. So the simplest one is C2H4, which we've seen already. And we talked about sigma and pi bonding. This is ethylene and hydrogens. Here we have sp2 hybridization, so we have one sigma bond and one pi bond. So the carbons and the hydrogens lie in a plane. This is 120 degrees. We've seen all of that before. The ethylene is the common name for it, but the name that's regulated by the International Union of Pure and Applied Chemistry is following this nomenclature. We take the ETH because C number is 2, and we add ENE. So the formal name for this is ethene, not ethylene, but you can use either one. No one's going to get very agitated about it. And then for n greater than 2, the position of the double bond is not fixed. Position of double bond not fixed. So we can show examples of that. Let's look at, here's one, butene. So C4H8. So one is to put the double bond at the very end. So I've just got one double bond in it. There's the 120 degrees, hydrogen, hydrogen. Now 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So this is C4H8. And this is called 1-butene because the double bond is off of the first carbon. Or we can put the double bond somewhere along the line, so we can do this. So the double bond is not at the very end. So we have a methyl group at the end. 1, 2, 3, 4. 1, 2, 3, 4. So this would then be called 2-butene. 2-butene, indicating that the double bond comes off of the number 2 carbon. So 1-butene and 2-butene turn out to be constitutional isomers because they got the same chemical formula, but they have a different mix of constituent groups. So let's label this as constitutional. These are both constitutional isomers. But we can zoom in a little bit more on 2-butene and be introduced to yet another type of isomer. So I'm going to redraw this because this has been drawn at right angles. It's colloquial. We know this thing is zigzagging and whatnot. So I want to redraw the 2-butene. And so I'll begin by putting the double bond. And then that means that I have to have 120 degree angles. And what turns out here is that the double bond goes to carbon, which has a hydrogen on one side, and on the other side it has a methyl group, right? And the same thing here. So now I have a choice. What I can do is I can put the methyl group up here and the hydrogen. All I've done is redraw this. All I've done is redraw the 2-butene. And I think you can see that I can put a symmetry plane here. I can put a symmetry plane, and what do I have? I've got both of my methyl groups above the carbon-carbon double bond, and both of the hydrogens below the carbon-carbon double bond. But another way I could have set up this structure, again, there's the carbon-carbon double bond. Let's put the 120 degree angles. We'll put the methyl group above the carbon-carbon bond on the left side, but below the carbon-carbon bond on the right side, and then we'll do the complementary positioning with the hydrogens. So in the case on the right, which is also a 2-butene, it's also a 2-butene, but we can see as 309-1ers, we look at structure. Structure is really important to us, and we say, okay, same constituent groups, but boy, you can tell the electron distribution is going to be different in the one on the left from the one on the right. So you start thinking, well, what about their properties? Guess what? They have different melting points. They have different boiling points. They have different density. You can see they're going to pack differently. So all of this, and yet they have the same chemical formula. So we have to distinguish these two. They're not different by their constitution, but they are different by their spatial layout. And the term that we use to talk about isomers that are different in their spatial layout, spatial arrangement, is stereoisomers. Stereoisomers. They are constitutionally identical, but structurally different. Right? Constitutionally identical, Identical constitution, different spatial arrangement. And so we've got labels on this. The one on the right to indicate that the various groups are on opposite sides of the double bond is called trans. Trans. So the structure on the right is trans-2-butene, where the one on the left is cis-2-butene. So now we've met stereoisomers, and we know what the... Oh, there's one other thing. We can have more than one double bond as well. We can have more than one double bond in an alkene, more than one double bond in an alkene. And we'll meet a few of these as well when we talk about polymers. If we have two, this is called a diene. And if we have three, it's called a triene. And we'll look at one of these. So for example, we could do something like this. Suppose I gave you CH2. You don't mind that I'm going to put the H on the inside? You'll forgive me? I mean, this is okay, right? So you know the H's are outboard, but we're just going to go with it. C, all right? What else? CH. Yeah. Okay, so what are we going to do with this one? I'm not going to give you this to name. I just want you to see how it works, and I'll make sure that we focus on the chemistry. But just for the record, 1, 2, 3, 4, 5. 5. So it's got to be pent. It's something pent. And it's got to be an ENE because there's at least one double bond here. And there are two. So this is going to be a pentadiene. A pentadiene. And furthermore, we can say this is carbon number 1, carbon number 2, number 3, number 4, number 5. And the double bonds issue from carbon number 1 and carbon number 3. So we could call this 1,3 pentadiene. So now you see how all of this works, and it's not so bad. Radicals. What happens if we want to use just a piece of one of these? So the only one that comes up well, there's two actually. One of them comes from ethylene or ethene. So I'm going to put the hydrogens to indicate when I don't have one. So I'm going to break this bond, throw away the hydrogen, and use this. So this is the radical that comes from ethylene. Well, you might say, well, why don't we call this, since the formal name, I'm going to use the UPAC name, ethene. Well, we can't say ethyl because ethyl's already taken. Ethyl is the one that's used over here for C2H5. So we need to distinguish this. And the name for this radical when we take ethylene or ethene is called vinyl. Vinyl. And we'll meet this one because if we want, we could then stick onto there, react it with chlorine, and then make, this is vinyl chloride. And then later on, we'll polymerize this, and we'll make polyvinyl chloride. So vinyl is the radical that comes from the compound ethylene or ethene. And then there's one other one that comes up in the life sciences a fair bit. If we look at propene or propylene, so that should be, it's got to have a 3. So 1, 2, 3. All right. So this is, if I lose one of the hydrogens here and make this into a radical, the radical that comes from propene can't be propyl because that's going to be C3H7. So here, this will be called allyl. Allyl. And as I say, this comes up sometimes in the life sciences, so we may find ourselves referring to that. So I'm giving you the direct path, the short course in organic nomenclature for our future work on polymers and on biochemistry. The last one, let's look at the right-hand column, which is also unsaturated. That's the alkynes. The alkynes, and these are characterized by sp hybridization. So sp hybridization. So these then are going to be hydrocarbons containing at least one carbon-carbon triple bond. This has the capability of carbon-carbon triple bonding. and it has the general formula CnH2n minus 2 for n greater than or equal to 2. And the main one that comes up that you're apt to meet is simply C2H2, which has the triple bond between the carbons. And the sp gives us 180 degrees. It's a linear molecule. And this, according to the nomenclature, should be ethine, because it's one of the alkynes. But you know this molecule as acetylene, which is used as a fuel in such things as welding torches. And obviously, the carbon-carbon triple bond has enormous energy in it. So that's one example. Okay, there's a few others. One is the aromatic hydrocarbons. We need to know those because we're going to meet those again. Aromatic hydrocarbons, and the UPAC name is arenes. These are arenes. And the prototypical one is benzene. Benzene is the main one that we need to know. And its chemical formula is C6H6, so it qualifies as a hydrocarbon. And people were mystified by its chemical structure, and it was Kekulé in 1865 who proposed the following structure. He proposed a hexagon of carbons with hydrogens off the corners, and then alternating double and single bonds. So double, single, double, single, double, single. And this is the way things lay until the 20th century, when, in the light of data, it became known from spectral evidence that, first of all, that all carbons lie in the same plane. All carbons lie in the same plane, and you can't have that if you've got alternating double and single bonds, because the single bonds are going to be coming out at something other than 120 degrees. And then the second thing that mystified people was the finding that all carbon-carbon bonds in benzene are the same length. All carbon-carbon bonds are the same length. So if the Kekulé structure is correct, you have the situation where the double bond is the same length as the single bond, and that doesn't sit well. And so we had to wait until Linus Pauling, who in 1931 proposed that, in fact, there are two structures. There are two structures that involve alternating between the structure that I've drawn here and the complementary structure where the double bonds move to where the single bonds are in the existing structure. So now we have two of these, and he said each of these is a hybrid. Remember, Pauling was the one who described hybridization in carbon in the first place. So these are hybrids, but they're hybrids of a different type. It's a mixing, and in fact, he proposed that the structure resonates between the two. So these are resonant hybrids. And sure enough, it's been found that the carbon-carbon bond length is on the order of about 1.47 angstroms. The carbon-carbon double bond is 1.33 angstroms generally, if you look in some of these alkanes. But in benzene, the carbon-carbon in benzene was found to be on the order of about 1.39 angstroms, which puts it in between. So if you take an average, we've got 3 double bonds and 3 single bonds. This is consistent with the notion of bond order 1.5. And so today, what people do to represent benzene is, rather than drawing these two structures or one of them and say figure out the rest for you, is to use a molecular orbital representation. Molecular orbital representation is as follows. We draw the hexagon and a circle inside. So this indicates the resonant hybrid that is present in benzene. And it's also present in a few other aromatics. And the other thing is that what happens in terms of electronic structure. I'm going to try to draw this. My drawing isn't the best, but you're stuck with me. What I want to do is to try to look at what happens in terms of the single and double bonds from the standpoint of formation with the various orbitals involved. And in particular, I want to look at what happens with the pi orbital. So 1, 2, 3, 4, 5, 6. Well, let's say for argument's sake that the double bond is where I've drawn it. So this means this is formed by the combination of a sigma bond and a pi bond. So the pi bond involves the smearing of these two pi orbitals. So let's indicate that with a little bit of fuchsia chalk. So there's a single bond next door. Now there's a double bond. And this double bond involves the smearing, again, of two pi orbitals, p orbitals, excuse me, to form a pi bond. And then lastly, there's a double bond across the lower left here. And so the pi orbital is formed. But when we realize that all 6 of these bonds are found to be identical in length, then everything is brought together so that we have equal spacing, at which point the electrons, all 6 of these, end up smearing. Hence this concept of electron delocalization. In other words, the electron is no longer confined to alternating pairs of p orbitals, but rather it's moving amongst all 6. So this can move through the entire structure. Right? And you can imagine if we then go back to graphite, then the electrons can move through the entire solid, which explains the observed electronic conductivity in graphite. And I think I've got a sketch right here to indicate. That's just a stick ball model of the stereoisomers. Okay, so there's a diagram from a book, and it's okay. So the artist that worked for the publisher did a better drawing than I did. All right, I accept that. I accept that. But you can see that the delocalization of the electrons here, and it doesn't just apply to something like benzene. It can apply in a straight line, and the recipe is for a conjugated electron system. And what they mean by that is alternating between double or triple and a single. Double or triple and then a single. So whenever you have multiple bond, single bond, multiple bond, single bond, you have the possibility of pulling everything in tight enough that the electrons can move from one multiple bond to the next multiple bond. So this is a conjugated structure, and here's one that's shown. This is a straight line molecule, and this one is I've just shown you a multiple bond in an alkene. So this is a 1,3-butadiene, where you have double bond, single bond, double bond, butadiene, 1,3, and what can happen is this can pull in so that we have a double bond here. So this is 2. This is a double bond. This is 1. 2 times 2, 2 times 2, plus 1. We have, this is essentially 5/3 average bond order through this linear molecule, and that's what you see up here. So you can imagine that happening in other systems where we have alternating single bonds, double bonds, single bonds, double bonds, or it can be even single bonds and triple bonds. Multiple, single, pulls everything in. And all of these will be called resonance hybrids when they allow the electrons to move as they do. Last thing is the radical. The radical here, if we take benzene, and now I'm going to indicate that this is the one that's got the missing electron, okay? So there's only one electron in the orbital. This radical, which is C6H5, is called phenyl. So we could take something like, let's build 2 of these. Let's take, here's ethene. And now I'm going to break one of these off, and I'm going to attach it to phenyl. So I can either call this vinyl benzene, or we could call it phenyl or phenyl ethene, right? Who's to say? Are you benzocentric? So you say that this is vinyl attached onto benzene, or maybe you're ethenocentric, and so you say this is a phenyl attached onto thing, but neither one of these are both correct, by the way, but we don't use this. This compound is called styrene. And what we're going to do later on is break this double bond, and we're going to make polystyrene. So that's styrene. And two others that I'd like you to be familiar with are, we can take and just simply add methyl groups. So if we take benzene and add one methyl group, this would be methylbenzene, or we could call this toluene. And there's the last one I'll introduce you to, and that's two methyl groups. Two methyl groups. So this is dimethylbenzene, or it's called xylene. And this whole sequence of benzene, let's just put benzene up here for completeness. So benzene, toluene, xylene, this BTX is used as additives to jet engine fuel to improve the octane number and improve performance. So let's move to that. So first of all, a little bit about Kekulé. Kekulé is an interesting person. He entered the University of Gießen to study architecture, but then he switched over to chemistry. And after his PhD, he moved to Britain. He took a job at St. Bartholomew's Hospital in London. And he would fall asleep on the bus going back to his flat. And the story goes that one day he fell asleep on the bus, missed his stop, woke up far beyond where he was supposed to get off. And during the course of that bus ride, it occurred to him in a dream that the way to describe the structures of some of the carbon compounds that were known at that time, people could characterize them by their molecular weight. So they knew what the structure was, but nobody until that time had the vision to suggest that carbon could link to itself and form a chain. So this is where he first proposes chains in 1855. And then he got a job as a faculty member at the University of Kent, went back to continental Europe, and one night he fell asleep by the fireplace, and he was dreaming about the benzene molecule. This guy really took his work home with him, okay? And so the story goes that he had this vision of a snake biting its tail and spinning in the dream. And that's where he came up with the idea of this Kekulé structure of folding. Remember, he already had the courage to put carbons in a line. So now he's going to fold that line over onto itself. And so he's really been considered the father of structural chemistry. And so I try to abstract, just keep the noise down. 3 more minutes and then you're gone. So what's his formula for success? Well, he moved into chemistry from another field. So sometimes this cross-fertilization is good. And the other thing is he's a dreamer. And I always tell people, you've got to keep dreaming. When you stop dreaming, you stop thinking big. But if you're going to dream, you have to get some sleep. I know people in this room don't sleep enough, so I'm going to challenge you to get some sleep, especially get a little bit of sleep on Tuesday night. I think you'll perform better on Wednesday if you've had some sleep on Tuesday night. The last thing I want to talk about is anti-knocking agents in automobiles and also in aircraft. If we took only straight chain alkanes for gasoline, they would burn very unevenly. Remember, in an internal combustion engine, you emit fuel as a vapor, you compress, and then you ignite. But after a number of firings, the engine chamber is hot, and if the fuel is too reactive, it'll ignite by itself as you're on the compression cycle. And you want staged compression. It has to be done in concert, on cue, not before its time. So this unprovoked firing is called knocking, and you'll hear that sometimes when you accelerate up a hill. You'll hear this pinging sound. Well, this is knocking. So the figure of merit that was introduced in 1927 is called the octane number. So it has an isooctane. See, it's trimethylpentane. Well, you know, that's 5 carbons, and the other 3 carbons to make octane are side groups. And they're off of the 2, 2, and the 4. And then compare that to heptane, which is absolutely abysmal. So this is 100, this is 0. And then you take whatever your gasoline is and you compare it against this standard solution. In this case, it's 90% of the trimethylpentane, 10% heptane. It ends up with an octane number of 90. Anything else that performs in the same manner. So when you go to the gas pump and it says octane 89 or whatever, that's where it's coming from. And you can use additives to increase octane. In fact, what you're trying to do is to repress ignition. High-octane fuel burns less well, but it burns on cue. That's the thing. So you could add tetraethyl lead, which was added for years. It's now banned. Or ethyl alcohol. Ethyl alcohol will raise the octane rating. And the way to make a mix of branched and cyclic alkanes is catalysis. You use a catalyst of alumina, silica, 450, 550 degrees C. It's called catalytic cracking. And so by catalysis, we can direct the synthesis to get the right mix of the right structures and thereby improve performance. Good luck on Wednesday.